Now that we've looked at the concept of determining whether or not a function is increasing or decreasing, and also how that can help us find max and minimums, we're going to look at this in a little bit more detail. First, just because my function is increasing, it's going up from left to right, that doesn't tell me everything, because here is a curve that's going up from left to right. Here is a curve that's going up from left to right. Both of them are increasing, so both of them have my first derivative to be positive. But both of these curves are doing something very different. Let's say this curve represents a profit function. Which one of these two curves, number 1 or number 2, would you prefer your profit to behave like? Well, I would say I would prefer my profit to behave like this function, because while my profit is going up in both instances, this one, my profit is getting bigger and bigger as I continue to go up. My profit itself as a function is increasing, but it's increasing at a faster rate as I move forward. Where here, if this were representative of a profit function, while my profit is going up at a slower rate as I move forward. And so just knowing that your function is going up, just knowing that your function is increasing, that the derivative is positive, isn't necessarily telling you everything. What you need to know is, okay, if the derivative tells you the slope, and I know that the slope here, 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 here is positive, is that slope, which is positive, getting bigger, or is the slope getting smaller? Is the derivative increasing or decreasing? The function is increasing, but is the derivative increasing? And in this case, in this example, my derivative is actually decreasing. While it's positive, the derivative itself is getting smaller, and that can be easily seen by the fact that the graph is steeper here than it is here. Well, if it's steeper here, the slope is bigger here than it is over here. So while my derivative is positive, it's also decreasing. Where here my derivative is positive, so my slope here, 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 they're all positive slopes, but the slope here is smaller than this, than this, than this, because the graph is getting steeper as I go, so my derivative is increasing. The function is increasing as well as the derivative itself. So from an application standpoint, again, which one of the two would you rather have your profit function behave like? I think everybody would prefer their profit function to go up, to increase, but how would you like it to increase? Would you like it to increase this way, or would you like it to increase this way? So getting even more detail about a function, whether it's increasing or decreasing, and how is it increasing or how is it decreasing, is important. And that's what this next section is all about, which we describe as something called concavity. So in this section, we discuss concavity. We talk about a function being concave up or concave down. So a function is considered to be concave upward on an interval if the derivative is increasing. Well, what does that mean? It means your derivative is getting bigger. Look at this curve right here. In this curve, if I think about what the slope is here versus here versus here, well, I can even extend the graph further this way. And I can say, well, if I look at the slope over here, the slope is negative. Look at the slope somewhere right around here, the slope would be 0. And then here, the slope is positive. Just from that aspect, I went from a negative to a 0 to a positive. Well, any number that goes from negative to 0 to positive is getting bigger. So the slope is getting bigger. The derivative is getting bigger. It's increasing. And so something that curves this way is considered to be concave up. If I just look at it from this section of the graph here, I have a slope that is positive here to a slope that's positive here to a slope that's positive here. But look at it, it's steeper up here than it is down here. So while these are all positive, the slopes are getting bigger. So concave upward means my slopes are getting bigger, or my derivative is getting bigger, which means my derivative is increasing. Conversely, if my slopes are getting smaller, look at this graph here. Here, my slope is positive. Somewhere around here, my slope is 0, and somewhere over here, my slope is negative. Well, if I go from positive to 0 to negative, I'm getting smaller. So my slope from here to here is getting smaller. My slope is decreasing. My derivative is decreasing, and we call that concave down. Even if I only look at this strip of the graph over here where the slope is negative the whole time, the graph is getting steeper and steeper as I go, but go on the downward trend, which means I'm going closer and closer to a negative infinity slope, so my slope is still getting smaller, but it's getting smaller in the negative direction. Either way, the derivative is getting smaller, the derivative is decreasing. So how your graph turns, either turning upward or downward, concave up or concave down, depends on what's happening with the derivative. Now, one thing to understand is when I draw this graph, this is the graph of the original function. So the original function has a derivative and a second derivative. The first derivative of this function tells me how this function is changing with regard to increasing, decreasing. It can also help me find max and mins. The second derivative as a function tells me how the first derivative is changing. In regards to the original function, it will tell me if the first derivative is increasing, then the original function is concave up. If the first derivative is decreasing, then the original function is concave down. So we have this little chart here, which describes the first derivative and the second derivative, whether each one is positive or negative, and how the original function graphically will behave. So the pink is the original function. So we have the derivative, and the derivative could be positive or negative. We have the second derivative, and the second derivative could be positive or negative. So let's say the first derivative is positive, which means the original function is increasing, and the second derivative is positive. So that would be this situation. So not only is my function increasing, it's going up, but it's also curving upward. On the other side here, we still have a function whose derivative is positive, but the second derivative is now negative. So while I'm going up, my graph is turning on a downward trend. So I'm moving upward, but I'm turning downward. So I'm increasing but concave down. That would be first derivative positive, but second derivative negative. Okay. Again, if we were talking about a profit function, we would prefer our profit function to at least look like one of these. This would be the optimal situation. What we would not like to see would be our profit function look like either one of these. Well, the first derivative would be negative. My function is now decreasing. I'm going down from left to right. But my second derivative could be positive. So while I could be going down from left to right, I could also be turning upward. And so that means that my function itself might be going down, but it's going down at a slower rate as I move forward. If I were to have a profit function that was going down, so I'd be losing money, okay, this would be the preferable way to lose money as opposed to this. This is just complete tanking. This one you're decreasing, so your derivative is negative. Your second derivative is also negative, so you're turning down. So not only are you going down, but you're going down at a faster rate and a faster rate as you go. So if your profits are doing this, you're pretty much out of business. So again, going up or going down is part of it, but how are you going up? Are you going up this way or are you going up this way? And you're going down, are you going down like this or are you going down like this? So how you go up, how you go down matters. Increasing, decreasing is part of it, but also concavity is some additional information that could be very helpful. Another way to look at graphical interpretation of concavity has to do with looking at the tangent lines. I don't particularly care for this method of looking at it. I think what I just explained does the job just as well, but it is another way of thinking about this. And so looking at concave up, if you look at each one of the tangent lines, if I looked at this point, there's the tangent line. If I look at this point, there's the tangent line. Look at this point, there's the tangent line. Each one of those tangent lines sits below the actual curve. Whereas if you look at a concave down picture, and I look at the tangent lines here, because the curve is curving downward, all the tangent lines are sitting on top or above the curve itself. So we could say a function is concave up if the tangent lines are above the curve, and if the graph lies above the tangent lines themselves are below. And it's concave down if the graph is below, so the tangent lines are then above. So then that brings us to what we call a point of inflection. A point of inflection is a point on the curve where the concavity changes. Now, so there's two things here you need. The concavity changes, but it's a point on the curve. So you could have a place where your concavity changes, but if you don't have a point there, then you don't have a point of inflection. So that's important to understand. The point of inflection needs two things. You need to have a point, which means the y value has to be defined, and the concavity has to change. So this point right here is a point of inflection. The graph is concave up on this side of that point and concave down on this side of the point. So that would be my point of inflection. Here's another point of inflection. I'm concave down on this side and I'm concave up on this side. So we have a point of inflection. Notice, whether I go from up to down or down to up, the point of inflection doesn't change in terms of what type it is. It's still a point of inflection regardless. We don't have like a different kind of point of inflection here versus here. We just label them all point of inflections. And here's another point of inflection where we go from concave up to concave down. So if you have a point where the concavity changes, you have a point of inflection. An example where that might not happen would be at a vertical asymptote. If you're concave up at one side of the vertical asymptote, but concave down on the other side of the vertical asymptote, okay, you could not have a point of inflection there. So just because the concavity is changing from upward to downward on either side of a particular x value does not guarantee a point of inflection. If your concavity changes and you have a point there, then you have a point of inflection. Where are these point of inflections going to exist? C f of c is going to be a point of inflection on the graph. If C f of c is a point of inflection on the graph, then that means that the second derivative was 0 or the second derivative didn't exist. When we talked about critical numbers, critical values, we figured out where the first derivative was equal to 0 or the first derivative didn't exist. But not every critical value would yield a maximum or minimum. This is essentially saying the same thing, that the only place that I could possibly have a point of inflection would be where the second derivative is 0 or does not exist. And in a way, you can say that if we found something that we could call maybe the critical numbers for the second derivative, then those would be the only places where we could possibly have a point of inflection. But not every critical number from the second derivative is a point of inflection. Now, when I say critical number, that's not really a used term as it relates to second derivative. If I were to say critical number, typically we're only using that term to define the first derivative being 0 undefined. If the second derivative is 0 or does not exist, we don't call that a critical number, although it is acting like the critical numbers did for the first derivative, in that it is a place where a particular derivative, whether it's first or second or third, is equal to 0 or does not exist. But again, you will never see a question say, find the critical numbers for the second derivative. If a question ever says, find the critical numbers, it'll basically be asking you to find them in relationship to the first derivative. Here, you could say, find the potential points of inflection for a function, which is basically asking you, where is the second derivative 0 or not exist. So if we're going to test for concavity, what we really need to do is we need to look at the second derivative being positive or negative. Go all the way back to where we were previously with increasing and decreasing. We looked at a function and we said this function f of x is increasing if the first derivative of that function is positive. And the original function would be decreasing if the derivative of that function is negative. So to determine if this function is increasing or decreasing, we looked at the derivative of that function to be positive or negative. So now what we want to know is the derivative increasing or decreasing? And that will help me figure out whether or not the original function is concave up or concave down. Okay? Sorry, I reversed that. Concave up or concave down. Okay? So we're going to take the derivative of the derivative, which will be the second derivative. And if the second derivative is negative, then the first derivative is decreasing, and the original function would be concave down. If the second derivative is positive, then the derivative itself is increasing, and the original function is concave up. So if the second derivative is positive, the original function is concave up. If the second derivative is negative, then the original function is concave down. So doing this example, determine the open intervals for which this function is concave up or down. In order to do that, I need to take the first derivative, which will then help me find the second derivative. Well, if I do the first derivative, I can use quotient rule. 0 for the derivative of the numerator, minus the derivative of the denominator is 2x times 6 all over x squared plus 3 squared. So that'll give me, this is 0. This will give me negative 12x over x squared plus 3 squared. Take the derivative again. That'll be my second derivative. The numerator would be negative 12 times x squared plus 3 squared minus the numerator, which is 12x. So that becomes positive 12x times the derivative of the denominator, which is 2 times x squared plus 3 times 2x all over x squared plus 3 now to the fourth. Something we're going to see happen a lot. There's a 12 here, there's a 12 here, there's an x squared plus 3 here, there's an x squared plus 3 here. I'm going to factor those out. So then what's left? Well, what's left is I still have this negative, and I'll still have an extra x squared plus 3. And then here I have plus, I'm going to have this x, I'm going to have this 2, I'm going to have this 2x, which is going to give me totally 4x squared all over x squared plus 3 squared, or sorry, to the fourth. This x squared plus 3 and one of these is going to cancel, giving me a third power. So bring that together, 12 times, distribute this in, collect like terms, you end up with 3x squared plus 3 over minus 3. Oh, that was a bad one. Minus 3, why? Because this negative distributes in here. Minus 3 over x squared plus 3 cubed. So there's your second derivative. So what we need to do next is to figure out when is the second derivative 0 and when does the second derivative not exist. Well, second derivative, since it's a fraction, will be equal to 0 when the numerator equals 0 and not exist when the denominator equals 0. However, this can never equal 0 because x squared plus 3 will never be able to get you a 0. It's a plus is the problem. However, this could equal 0 when x equals plus or minus 1. And so we have two critical numbers, plus and minus 1. So what we're going to do is we're going to set up a little chart for the second derivative. -1 and +1 would be my values. I'm going to then pick a number from the interval. All this looks exactly with what we were doing before with first derivative. We're just now doing it with second derivative. And so if I plug each one of these numbers into the second derivative, which is right here, and see what kind of answer I get for the second derivative, that'll tell me whether the original function is concave up or concave down. So look at the denominator. If I plug anything into this denominator, I'm going to square it, add 3, then cube it. Well, square it and then add 3 will give me a positive value, and then cube it will be positive. So the denominator doesn't really affect whether the whole thing is positive or negative. Only the numerator will. So if I plug -2 into the numerator, I'm going to get 4 times 3 is 12. Minus 3 is, what do you get? 9. And so what you end up with is positive value over a positive value. So you get a positive. If I plug 0 in, I'll get a negative. If I plug +2 in, I get a positive. So what does that tell me? The fact that the second derivative is positive tells me that the first derivative is increasing, which tells me that the original function is concave up. If the second derivative is negative, it tells me that the first derivative is decreasing, which tells me the original function is concave down and then concave up. So the question said, determine the intervals where we're concave up and concave down. This table here is not the answer. We take that table and we get the answer. So we would say f of x is concave up on the interval from -infinity to -1 and 1 to infinity. F of x is concave down on the interval from -1 to 1. And so that answers the question about the original function's concavity based off of looking at the second derivative. Notice the process is very similar to what we did for increasing and decreasing in max and mins. We are just doing it with the second derivative. Labeling this chart with a f double prime is important because f double prime being positive and negative tells you something than f prime being positive and negative. And understanding that this chart and the other chart give you different information about the original function is going to be key. Okay, so we want to find the points of inflection and concavity for the following function. Now the nice thing about this one is the derivative as well as the second derivative are very easy to find, being that it's a polynomial. So we find f prime, and we're going to get 4x cubed minus 8x. We find f double prime, and we're going to get 12x squared minus 8. So now in order to find points of inflection and concavity, this all has to do with the second derivative. So we need to figure out when the second derivative equals 0 and when the second derivative does not exist. Being that the second derivative is a polynomial, this quadratic polynomial, we don't have to worry about does not exist. So mainly we're just focused on when does 12x squared minus 8 equal 0. Well, move the 8 by adding it, divide by 12, you get x squared equals 8 over 12, which is the same thing as 2 over 3. So x equals plus or minus the square root of 2 over 3. So there are two critical numbers. So in looking at these critical numbers, you can go, okay, let's set up our plus minus chart. I have negative square root of 2/3, positive square root of 2/3. Don't be thrown off of the fact that it's a square root of 2/3. It's not the nicest looking value for your second derivative equal to 0. But we are working with the second derivative. So I'll plug in -1 will be over here, 0's in the middle, 1's over here. I'm plugging these all into the second derivative, which is here. And I think clearly you can see when I plug -1 in, I'm going to get a positive. When I plug 0 in, I'm going to get a negative. When I plug +1 in, I'm going to get a positive into the second derivative. Again, because this second derivative is a pretty easy function. So what does that tell me? It tells me my original function is concave up, concave down, then concave up. As far as points of inflection goes, these could be points of inflection as long as they are points to begin with, because the concavity does change from up to down, but they have to be able to be points on the function itself. Since this function is a polynomial function, they sure are points. And so if we found f of negative root 2/3, it would be the negative square root of 2/3 to the 4th minus 4 times negative root 2/3 squared. Well, essentially, 4th power is to square this, then square it again. If you square it once, you get 2/3, then you're going to square it again. Minus 4, you square this, you're going to get 2/3. Square it again, you get 4/9, minus this will be 8/3. Doing the subtraction, multiply this by 3 over 3. You see you're going to get 4 minus 24, which would be negative 20 over 9. If I did f of 2/3, or root 2/3, since I'm raising it to the 4th power and 2nd power, it's the same as negative, so this will also be negative 20 over 9. So what could we say? Well, we could say f of x is concave up on the interval from negative infinity to negative root 2/3, and the interval from root 2/3 to infinity. We can say that f of x is concave down on the interval from negative root 2/3 to positive root 2/3. And we can say that f of x has points of inflection at negative root 2/3, negative 20 over 9, and positive root 2/3, negative 20 over 9. 20 over 9. Okay. So the question said determine the points of inflection in concavity. We did all that simply by looking at the second derivative. Again, another question, determine the open intervals for which the function is concave up and concave down. Now this question didn't ask about points of inflection, but I'm going to throw that in. And find points of inflection. Okay. So we need the second derivative. Now this one's going to be a little bit trickier to find the second derivative simply because we're going to use quotient rule here. So first derivative. Derivative of the numerator is 2x times the denominator minus the derivative of the denominator is 2x times the numerator all over the denominator squared. Multiply that out. This times this, this times this. You see you're going to get 2x cubed. You're going to get minus 2x cubed. They'll cancel. This times this will give you a minus 8x, and this will give you a minus 2x. So we're at minus 10x over x squared minus 4 squared. Okay, that's first derivative. Second derivative. Derivative of the numerator, do quotient rule again. Derivative of the numerator is negative 10 times x squared minus 4 squared minus negative 10x, which would give us positive 10x, times the denominator's derivative, which would be 2 x squared minus 4 to the first times 2x all over the denominator squared. So now we're at x squared minus 4 to the fourth. And this is where we're simplifying. Notice we have a 10 and a 10, and x squared minus 4 and x squared minus 4. So I'm going to factor those out. So you have 10 times x squared minus 4, and we would be left with this negative and another x squared minus 4. So negative x squared minus 4 plus, we're going to have this x, this 2, and this 2x. So that's going to give us plus 4x squared all over x squared minus 4 to the fourth. So in total, these x squared minus 4's cancel. So I have 10 times, this will be 4x squared, this will be a minus x squared, so that gives me 3x squared plus 4 all over x squared minus 4 to the third. So that is my second derivative. Now what I want to do is find when does the second derivative equal 0 and when does the second derivative not exist. Well, being that it's a fraction, equal to 0 when the numerator equals 0. Looking at this numerator, this is 10, that's never going to be 0, and 3x squared plus 4, since we have a plus, that actually is never going to equal 0. So now we don't worry about this one, but the denominator could be equal to 0 when x squared minus 4 equals 0, which would be when x equals plus or minus 2. So we still have two critical numbers on this one. So we lay out our critical numbers. We have -2, we have +2. We're looking at the second derivative. And we're going to take -3, let's go 0, let's go +3. And we're going to plug it into the second derivative. Again, notice the numerator is 10 times 3x squared plus 4. Each of those will be positive no matter what x value we plug in any of these intervals. So if the numerator is always positive, we're really just concerned with the denominator. And if the denominator is also positive, the whole thing's positive. If the denominator is negative, then the whole thing's negative. If I plug -3 in here, I'm going to get 9 minus 4, positive. If I plug 0 in here, I'm going to get 0 minus 4, which is negative. And if I plug 3 in again, I'm going to get a positive. So that tells me concave up, concave down, concave up. As far as points of inflection goes, these two could be possible points of inflection, as long as they are points on the original function. But look, if I try to plug -2 into this original function, or +2 in, I'd have a problem with the denominator being 0. So these are not points of inflection. In fact, if you look closely, they're vertical asymptotes on this original function. So as far as concavity goes, we could say that f of x is concave up on the interval from -infinity to -2 and 2 to infinity, and is concave down on the interval from -2 to 2 and has no points of inflection. Then this brings us to the second derivative test. What we were just doing was not the second derivative test. Ignore this example right here. What we were doing was not the second derivative test. What we were doing was determining concavity. What the second derivative test talks about is a way to find maximums and minimums using the second derivative. Now, we talked about the first derivative test, and in the first derivative test it says that if your function switches from increasing to decreasing, then you could possibly have a maximum as long as the point is defined. If your function switches from decreasing to increasing, you could have a minimum as long as that point is defined. How do we find increasing and decreasing? We find it by looking at the first derivative. First derivative positive, first derivative negative. Okay. We also find the place where this point and this point could be located by finding when the first derivative is 0 or the first derivative does not exist. So maximums and minimums are initially found by first looking at where the first derivative is 0 or does not exist, and then from those critical numbers, which we called these two locations critical numbers, from those critical numbers we then tested them using the first derivative and looking at the sign of the first derivative to determine if these critical numbers were in fact max and mins. What second derivative test is going to say is that we're going to first find the critical numbers from the first derivative, which is we're going to find where the first derivative is 0 or does not exist. But instead of using the first derivative to then additionally test those critical numbers, we're going to use the second derivative instead. So again, we're still finding the critical numbers from the first derivative because that is where we could possibly have a max and min. But instead of continuing to work with the first derivative and figure out where the first derivative is positive and negative and where it switches, we're instead going to look at the second derivative. What this says is that if we take a critical number from the first derivative, and let's call that c. C is a critical number from the first derivative. And we plug c into the second derivative, and it is greater than 0, which means we get a positive answer. Then that critical number will result in a relative minimum as long as that point exists. Here's the other part. F has to exist. Okay? If we plug that point into the second derivative and get a negative, then f is going to have a relative maximum at that point as long as it exists. And thirdly, third thing here is that if we plug it into the second derivative and get 0, the test fails, which means we're not going to be able to use the second derivative test, and we're just going to go back and use the first derivative test anyway. Now look at this a little bit closely. So I said greater than 0 minimum. So greater than 0 minimum, positive but a minimum. That doesn't seem to make a whole lot of sense. You would think positive maximum, right? But that's not necessarily the case here. So second derivative being positive results in a minimum. Second derivative being negative results in a maximum. Now why is this? If your second derivative is positive, it tells you that this critical number is located on a concave up picture. Okay? So second derivative is positive, your function is concave up. If your critical number is located on a concave up picture where your graph is turning upward, then by default this point would have to be a minimum point since the graph is turning upward around it. If your second derivative is negative, that automatically tells you that the function is concave down. And if the function is concave down, then this critical number that you found using the first derivative is sitting on a concave down portion of the graph. And if it's sitting on a concave down portion of the graph is turning downward around it, thus making this point a maximum. Now the fact that this test fails is the only problem with the second derivative test, in that there are some instances where we can't use the second derivative test, and therefore would just go back to using the first derivative test, which also always brings up the question, why would we use it if we could just do everything with the first derivative test? Well, computationally, sometimes it's easier to use the second derivative test than the first derivative test, because computationally, sometimes the second derivative is an easier function, sometimes not though. And so all this is an additional way to help you find maximums and minimums. Whether you decide to use it when the time comes or not is up to you, but we can use both the first derivative or the second derivative to help us find relative maximums or minimums. Again, they only come from the critical numbers of the first derivative, but whether we additionally test those critical numbers from the first derivative using either the first derivative or the second derivative doesn't necessarily matter. So here's a quick question that we can use to apply the second derivative test. Here's a function, and we want to try and use the second derivative test to find our relative extrema. First thing we want to do is find the first derivative. In finding the first derivative, we're going to get 6x squared plus 6x minus 12. Now what we want to do is find critical numbers from the first derivative. So we figure out when is the first derivative 0, when does the first derivative not exist. Being that the first derivative is this quadratic polynomial, we don't worry about does not exist, but it could be equal to 0. That will be easy to find. Factor out a 6, we get x squared plus x minus 2 equals 0, which will give us x plus 2, x minus 1. So when x equals negative 2 and when x equals positive 1, these would be our critical numbers or critical values. So these are the two places where we could possibly have relative extrema. Now, the question is, are they relative extrema? And if so, what kind? We can then start using our table, lay these out, and look at the first derivative and determine, plus, minus with each one of these and see what happens, increasing, decreasing, whatever. But we're not going to do that right now. That's the first derivative test. We want to use the second derivative test. So what the second derivative test says is, okay, find the second derivative. Very easy to do here, which would then be 12x plus 6. And what we're going to do is we're going to evaluate the second derivative at each of these critical numbers. So -2 and 1. If you plug -2 into the second derivative, notice you're going to get a negative value. If I plug 1 into the second derivative, I'm going to get a positive value. Since I have a negative value, if the second derivative is negative, I'm on a concave down picture. And if I want a concave down picture, then that point should be a maximum point, as long as this x value can be plugged into the original function and give me a point. Second derivative is positive, means I'm on a concave up picture. If I want a concave up picture, then that point is then going to result in a minimum, as long as the function is defined. Now clearly this function being a polynomial will be defined, so this tells me I have a relative max at 1, say f of 1, whatever f of 1 ends up being, plug 1 in here, here, and here, you can find f of 1, and a relative min at -2. Oop, I reversed these completely. This one is actually a minimum. So a relative minimum at 1, 1, and a relative maximum at -2 f of -2. So again, minimum here, and max. Okay. And so that's how your second derivative test works. We could have very well gotten the same thing by using the first derivative test, but I wanted to get some practice in the second derivative test. Finally, what we can do is put everything we've learned between the first and second derivative together to sketch out the entire graph. So put all of it together. And we could also use a lot of the stuff that we learned in pre-calc to do this as well. So take everything you learned in pre-calc, take everything we learned in calc so far, and put it all together. You can analyze and sketch the graph very well. So first, take a couple of things you learned in pre-calc. I think most importantly, you start with domain. What is the domain for this function? Well, you know that the denominator can't be 0, which would be the domain is the set of all x such that x doesn't equal plus or minus 2. So those are two x values we absolutely cannot have in this function. Every other x will be defined. A couple other things. This is a rational function. Another important thing about rational functions are your asymptotes. This thing will have a vertical asymptote when x equals plus and minus 2. And that goes hand in hand with the domain. The denominator will be equal to 0 when x equals 2 or -2. The numerator will not. If the denominator is equal to 0 only, you have your vertical asymptotes. There's also a horizontal asymptote. And so your horizontal asymptote will be based off of the degree. Top and bottom are the same, so y equals 2. If we look at the leading coefficient, 2 over 1, horizontal asymptote will be y equals 2. So all that's some real basic stuff you would have learned in pre-calc. You learned a lot more than that in pre-calc, but that's just a couple of quick things we can do to get this thing started. We could look at looking at the x-intercepts, the y-intercepts. We could look at symmetry. I mean, we could talk about the range of this function. But to get this thing moving a little bit quicker, we're going to now jump into our derivatives. And so if we found the first derivative for this function, that's pretty easy. The 2 is a constant multiple, so I'm going to take that out. And I'm going to look at this function here. And I'm going to do the quotient rule. So 2x times x squared minus 4 minus 2x times x squared minus 9 all over x squared minus 4 squared. Multiply all that out, 2x in here, 2x in here, cancel. You see you're going to get minus 8x, and you're going to get a positive 18. So minus 8 plus 18 is going to give you 10x over x squared minus 4 squared. So there's your derivative. So we want to figure out when does the derivative equal 0, when does the derivative not exist. So equals 0 when the numerator equals 0, which will be when x equals 0. Does not exist when the denominator equals 0, which will be when x equals plus or minus 2. We have 3 critical numbers. In laying out these critical numbers, we're going to determine increasing, decreasing, max and mins. That's all the information we can get out of the first derivative. Okay, we're looking at the first derivative here. So we can determine where this original function is increasing, decreasing, and also then use that to help us find our maximums and minimums. So we set up our chart. We'll look at -3, let's go -1, 1, and 3 into the second derivative, or first derivative, sorry, first derivative. The denominator is a square, so the denominator is always positive. So we're really just looking at the numerator. We plug in -3, that is negative. We plug in -1, it is negative. We plug in +1, it's positive. We plug in +3, it's positive. So this tells us that our function is decreasing, decreasing, increasing, increasing. So we'll write that out. F of x is decreasing from -∞ to -2, -2 to 0, increasing from 0 to 2, and 2 to infinity. Okay. As far as max or mins go, this is the only point where we could possibly have a max or a min. As long as we can take that and plug it into the original function, we'll look at f of 0. Can we find f of 0? Yes, if I plug 0 in here and here, I can do that. Plug 0 in there and there, I get the point 0, 18 over 4, so it's going to be 9 over 2. And this will be is a minimum. So all this came out of the first derivative. We have where the function is increasing, decreasing. We also have a minimum point, and there are no maximums. Next thing we want to do is we want to find the second derivative. I mean, based off of this, we can really do a lot. But the second derivative will give us just a little bit more information. So now we go with the second derivative. Okay, computationally, that's going to be a little bit more work, but we can do that. This 2, and even we can even say the 10, but let's just say the 2. 2 is a constant multiple again. So I could take the derivative of the numerator, which would be 10, times x squared minus 4 squared, minus 10x times the derivative of the denominator, which would be 2 x squared minus 4 times 2x, all over x squared minus 4 to the 4th this time. And so we have 2 times, I'm going to factor the 10 out and the x squared minus 4 out. So we have times 10 times x squared minus 4 times, well, what's left? There's going to be an extra x squared minus 4 minus, there'll be an x, a 2, and another 2x. So that'll be 4x squared all over x squared minus 4 to the 4th. I can cancel this with one of these. This can come together, and I would get 2 times 10 times negative 3x squared minus 4 all over x squared minus 4 cubed. So then what we're looking for is when is this second derivative 0 or does not exist. Okay. Being a fraction, numerator equal to 0, denominator equals 0. Well, this one's easy. This will be x equals plus or minus 2. This one here, numerator equal to 0. Well, if you look at the numerator, you're really only looking at this piece because the 2 and a 10. Is it possible that negative 3x squared minus 4 could equal 0? Well, that would mean x squared would have to equal negative 4/3. That can't happen. So we don't worry about that. So we only have two critical numbers. So we'll look at these critical numbers, negative 2 and 2, in the second derivative, and this will determine concavity as well as points of inflection. So plugging these into the second derivative, we'll go negative 3, we'll go 0, we'll go 3. We're going to plug them into the second derivative. If you notice, this piece here, no matter what x we plug in, is always going to be negative. Times 2 times 10. The numerator is always negative. If the denominator is also negative, then the whole thing is positive. Well, if I plug in negative 3 into the denominator, I get 9 minus 4. That's positive. So negative over positive will give me a negative. 0 will make the denominator negative. With the negative in the numerator, that would give me a positive. And the last thing will give me a negative. So what does that tell me? It tells me my function is concave down, up, down. So let's write that out. F of x is concave down from negative infinity to negative 2 and 2 to infinity and up. I should say concave up. I'm running out of room here on negative 2 to 2. All right. So we found everything we could possibly find based off of what we've learned so far. Now it's time to put it together to draw the graph. Okay, we have x can't be these values, which results in these two vertical asymptotes. We have a horizontal asymptote. We have a minimum. We have increasing, decreasing. We have concavity. So if we put that all together, draw our xy plane. Negative 2 and positive 2 are our vertical asymptotes. We had a minimum at 0, 9/2. So let's say 0, 9/2 would be right here. We know we had a minimum there. We had a horizontal asymptote at 2. So let's say a y of 2 would be here. And so we talked about this thing. Let's look at it between negative 2 and 2. Between negative 2 and 2, we said that it was concave up. We said we had a minimum here. We said it was decreasing from negative 2 to 0 and then increasing from 0 to 2. All that comes together to give me that piece. Then from negative infinity to negative 2, we said our function was concave down. If you go all the way back, we also said it was decreasing. So if it's decreasing and concave down, our graph would look like this. Conversely, if we look at the other side, we said our graph was concave down from negative 2 to infinity, but we also said it was increasing. It was concave down but increasing would give me this picture. All the while remembering that how your function should behave around your vertical and your horizontal asymptotes helps us further understand why the graph would look like this. So this would be the graph of this function, putting together all the pieces that we just computed.